Well, hey guys, welcome back to, well, this is not my bench. I'm 400 or so miles north, way up in Michigan. I think I found a bench that is messier than mine. Look at this. Oh my God. Belongs to this guy here. Antone, buddy of mine, come up here to have some fun, ride bikes and sightsee and all that. But I'm going to try to collaborate on a video. What we're going to talk about today is how to calculate source resistance, also known as source impedance, if you will. But what is source resistance? Well, there's kind of a parasitic resistance inside power supplies, batteries, and things like that. Except, of course, for regulated power supplies, and there even can be some considered in those. So we'll have a little diagram here. This is representing our power source. It has a fixed voltage source. So no matter what load we put on it, it's always going to be fixed. But there's this parasitic resistance inside. Over here on the power source or power supply side of the switch is a voltage meter we use to measure the voltage. On the other side of the switch is our load. So what we do here is we measure the open load voltage, and then we measure the voltage when it's loaded. Okay, I have an example circuit set up with actual values, and we'll come up with the formula and everything to calculate it. So we have 12 volt voltage source, and we have the meter connected and a 5 ohm resistor. With the switch open, so there's no load, we'll measure 12 volts because there's no current. Yeah, somebody's going to say, well, you might get a little bit of current through the meter, but for all intents and purposes, the meter is a very, very light load. It's not going to affect our circuit or our voltage. So now when we close the switch, current is going to flow through this resistor, this 5 ohm resistor. And when that happened, we measured 11.5 volts. So the power supply has a voltage drop in it due to this resistor, or inside is like an ESR, equivalent series resistor, I guess you could say, or a parasitic resistance inside this power supply. Now we need to calculate what that resistance is, and this is how we do it. Is that Snickers? No, he's purring too loud. It's a counterfeit Snickers. No, it's Charo. Charo the kitty. Even up north, I have a little kitty. Well, it's time to apply a little bit of Ohm's Law. Well, we have some voltages and we have a resistance. We need to know current, and we need to know the difference in voltage, loaded and unloaded. Okay, well, first we just take the unloaded voltage minus the loaded voltage. That cat purrs so loud. Man, listen to that cat going. So it was 12 volts minus 11.5. That's half a volt. Next we need to calculate the current. Well, loaded, we know it dropped to 11.5, so that's going to be the voltage drop across this resistor, 5 ohm resistor. Ohm's Law again. Ohm's Law is very easy. It's always voltage on top when you're trying to find current or resistance. In this case, we're trying to find current. 11.5 divided by 5 ohms, 2.3 amps. We have everything we need because current in this part of the circuit is going to be the same going through the load resistor. So it's half a volt divided by 2.3. Again, Ohm's law. Voltage on top, we're trying to find a resistance. Current on the bottom, 0.217 ohms. So we have measured what the series resistance is. So what we did here is we solved it in steps, but you can also write it as a formula. I'm just taking the no load minus the loaded voltages, put them down here, and the equation, the loaded voltage divided by the load resistance, which is just an Ohm's law equation, put it down in the denominator, and that's the equation. Now, who in the hell remembers this stuff? What I do, I like to solve things in steps. You need just Ohm's law. It makes it a lot easier. It's just the way I do it. But if you want an equation, that's the equation. Okay, well, that's finding the source resistance. Now we're going to apply it. Okay, let's put this to the test. We set up a circuit here. We have a voltage source. The source resistance, which we covered up, we know what it is, but we're going to see if we can calculate its value. And the load resistance, which I think is 330 ohms. I guess I can't see that, but we'll go ahead and we got a what is it, orange brown?
Looks like it.
Yeah, that's what I thought I picked. Okay, we have a power supply hooked up, which is supplying power. This is a 7806 6-volt regulator, and we're already measuring the unloaded output. And well, go ahead and measure the unloaded output. Anton, my lab assistant here. And
605.
605. Okay, go ahead and load that down. Connect the load resistor up. The calculator here.
Okay, now we are at 5.84. 5.84344.
6.05 minus
5.84. Well, it's half between, so 5.835.
we'll just say. Okay, so we have
Solid on 3 now.
voltage drop of 210 millivolts. Okay, so we measured 210 millivolts, 5.84 volts loaded, and of course 6.05 unloaded. Now I need to know the current through that resistor. Okay, I had that written down wrong. It's 1.77 milliamps. Okay, so what we need to do to figure our source resistance, divide this voltage, which was the difference voltage, by that current, because current's going to be the same in every part of that circuit. So Anton, if you would do the honors, and 0.21 divided by 0.0177. And he gets
11.85, well, 86.
11.86 volts. And do the honors and peel that tape off the resistance, or the resistor there.
Oh, they tucked it in and made it hard.
And it is, focus camera please, 10 ohms. So yeah, there was some error because the voltage does change a little bit. I think it was 6 volts when it was under load, from our so-called voltage source. So it did change a little bit, but you can see how you can calculate the source resistance. Now we're going to do another test. We're going to find the impedance.
Well, the tolerance on the resistors has got to be considered too. That's probably part of the issue. I want to see one thing. Under load, our 6 volts is exactly
6 volts flat.
Or unloaded, it was like 6.05. Okay.
Yeah.
All right. Excuse my stroke.
Yeah, so we have to consider these are 5% resistors, and our voltage source did change a little bit. It was 6 volts flat under load and 6.05 unloaded. So that does throw off the numbers a bit. Was hoping it would come out closer, but you know, it did get us in the ballpark. Well, I'm back at home at my own messy bench. Been about a week since I shot the first part of the video up in Michigan. I wanted to redo the test example with the voltage regulator. The other one, it just seemed like it was off too much. It was like 11.8 or something ohms. Just figured I should get a little bit closer. One thing with these voltage regulators, if you run them open load, you might have more of an error. They should have a minimum load put on them. So this resistor here is not part of the circuit I'm measuring. It just puts a load on the output of the regulator. So I have a 10 ohm resistor, and I'm using a 470 here as the load. This will be our source resistance. Ignore this other stuff, it's part of another circuit. I made the power supply in the other video for the amplifier. But anyway, I went ahead and took measurements, and this was the open load voltage, and this was the loaded voltage. That was the difference voltage, and this was the current going through the load resistor, which also would be going through the source resistance. And having these two numbers now, I can calculate the source resistance, and that comes up very close, 9.994 ohms, and that was a 10 ohm resistor. So let's measure that now. 0.99 ohms. So yeah, we're pretty darn close. Let me check the load resistance. Used a 470. It's a little low, but you know, it's not enough to really throw the thing. I already checked the voltage on the regulator. It did not change with loaded down and open load. So yeah, we have a pretty darn good test here. So that's it for part 1 of the source resistance video. Stay tuned for part 2 where I put this to use. Thanks for watching.